as promised, I'm going to provide a couple of short videos introducing some new ideas for the next homework. And the first is the idea of similarity between matrices, in particular for square matrices. So the motivating question that we're going to ask is when two different matrices have the same eigenvalues. And we're not going to give an if and only if characterization, but we'll provide some sufficient conditions for when two matrices will have the same eigenvalues. And one thing I want to point out is this will not ensure that the two matrices will have the same eigenvectors, as you'll see in the proof, which I delineate below. So I'm going to try to be concise because I'll come back to this next week and we can talk about it in a little bit more depth. And I don't want to make these videos too long. So again, the question we're asking is, given two matrices A and B, when can we ensure that they have the same eigenvalues? You can sort of think of this in two ways. Given the matrix A, we're going to be able to produce a class of matrices that share the same eigenvalues of A. We talk about two matrices being similar and we use this symbol, when there exists some other invertible matrix so that the following holds. So this is called conjugation. It's the same essential idea as conjugating in other contexts in mathematics, but two matrices A and B are similar if A equals P, B, P inverse. So multiply on the left by P, on the right by P inverse, and all we need is for this matrix P to be any invertible matrix. So notice that if A and B are similar, then of course B and A are similar, because if I left multiply by P inverse and I right multiply by P, then I have the exact same relation, except B will be equal to P inverse A P, and since P is P inverse inverse, by definition of similarity, then if A is similar to B, then B is similar to A. So it's not quite equality, but it's what's known as an equivalence relation in mathematics, and we study equivalence relations in Math 300 if you're interested in taking that class. So in any case, two matrices are similar if they have this property, and of course you can write it in this way. So if you right multiply this identity by P, you get AP equals PB. So what I want to show you here is that similar matrices, and this is a theorem, similar matrices have the same characteristic polynomial, and if they have the same characteristic polynomial, then they have the same eigenvalues. So this is what I want to show you, and I'll remind you that if you subtract A minus lambda I forgot an I here, and you take the determinant of if A is an n by n matrix and you subtract off lambda times the n by n identity, then this will end up being an nth degree polynomial, which you can subsequently factor, and that polynomial is called the characteristic polynomial. When you set it equal to 0, that's called the characteristic equation. And from our reminder slash refresher about eigenvalues, we know that in order for a matrix to have an eigenvector, that eigenvector has to correspond to an eigenvalue. That eigenvalue is a root of the characteristic equation. In any case, let's come up here. So what I'm going to do is I'm just going to start with a similarity relation, and I'm going to subtract off lambda I. So if A equals PB P inverse, then A minus lambda I is PB P inverse minus lambda I. And I just did some manipulations here, which I'm not going to go through, but I'll just point out that when you subtract off lambda I, you can always write I as PP inverse, if P is invertible, but that's what we're assuming, because we're assuming that these matrices are similar, so there's already this fancy matrix P. And so then, since lambda here is a constant, and scalars move through matrices, through linearity of matrix multiplication, I'm going to scooch this lambda over, and then I'm going to expand lambda as lambda times I. This is legal, because the identity times any matrix is itself, so this is fine. So all I've done is, again, taken this, subtracted lambda I from both sides, that's the first line, written the identity as P times P inverse, that's legal, moved lambda around and inserted an identity. The identity doesn't do anything, so that's legal. And then I'm just going to left factor by P, because there's a P here and a P here, and that allows me to use linearity. And I'm going to right factor by P inverse, which is legal by linearity. So I have B minus lambda I, P inverse. So what you see is that A minus lambda I can be written in this way. So in other words, if A is similar to B, then A minus lambda I is similar to B minus lambda I. Now we're just going to take determinants, and the reason, again, as we talked about before, is that to find the eigenvalues of A, I need to find the characteristic polynomial. If I want to find the eigenvalues of B, I need to find the characteristic polynomial of B minus lambda I. So I take the determinant of both sides of the equality, I use the multiplicative property of the determinant, so the determinant of ABC is determinant of A times determinant of B times determinant of C. Once you take the determinant, the value of the determinant is just a scalar, so these can be rearranged. That's what I wrote here. Why? Well, because each of these three quantities is a real or complex number, so we can rearrange them. And then from the exercise we did in class last week, the determinant of P inverse, if P is invertible, is 1 over the determinant of P, which means these cancel. And so if we've identified that the determinant of A minus lambda I is the same as the determinant of B minus lambda I, then that means that A and B have the same characteristic polynomial. If they have the same characteristic polynomial, the polynomials have the same roots. If they have the same roots, then accordingly they have the same eigenvalues. So this is the idea of matrix similarity, and what we've proven, which I should have written out and didn't, is that if A is similar to B, then the eigenvalues of A are the same as the eigenvalues of B, being very careful because that does not mean that the eigenvectors of A are the same as the eigenvectors of B, but that the eigenvalues are the same. And I just gave you an example down here. So I didn't do the work. In some of the subsequent examples, I'll do more of this work, but I just picked a random matrix, and what I claim, and you can check me on this, in fact I'd like you to, is that this 3 by 3 matrix is similar to this 3 by 3 matrix, which means there has to exist some invertible matrix so that when we conjugate one of these by that invertible matrix, we get the other. So I'm claiming that A is similar to B via this invertible matrix P, although that doesn't look right because that looks exactly the same as this one. Let's see. Well, in any case, let's verify this claim, but you can try to use this matrix as well. Okay, so in the next video, I'm going to talk about diagonal matrices, and we're going to talk about the process of diagonalization.